Hi, I'm Ali. Today's problem is about university courses and how we choose them. It's called Course Schedule 2 and is a common interview question, but it's not really that complex. It's been mostly asked by Amazon, Microsoft, and Oracle. So, let's take a look at it.
The question says there are a total of n courses, and they are labeled from 0 to n-1. Some courses may have prerequisites. So, for example, if prerequisites index I equals to AIBI, what does that mean? This means that we must take course BI first, then AI. So BI is kind of a prerequisite for AI. So it says, given the total number of courses, which is called num courses, and a list of prerequisite pairs, which is the prerequisites array, we have to return the ordering of courses we have to take to finish all courses. So we have to return the ordering, the suitable ordering to take all courses. And it also said that if there are many valid answers, so it means that we may have more than one correct answer, so we have to return any of them. And it is also impossible, if it is impossible to finish all courses, we have to return an empty array. And it gave us also several constraints over the variables that you can see here. But I think these two are the most important one, that AI and BI are not equal, and all the pairs in the prerequisites array are distinct. So let's see and solve several examples to understand this question better. In the first example, the number of courses are 2, and the prerequisites or prereq array looks like this. So we have 2 courses, and this, based on the definition that the question gave us, this means that course 0 is a prerequisite for course 1. So the output, which is the suitable ordering, would be 0, 1. Or it's better to show it in an array. So it's 0, 1. That means that we have to take course 0 first and then 1 in order to finish all courses. In the second example, the number of courses are 4, and the prereq array looks like this. So let's analyze this array. It means that course 0 is a prerequisite for course 1, and 0 is also a prerequisite for course 2. Course 1 is a prerequisite for course 3, and course 2 is also a prerequisite for course 3. So this means that when we pass course 0, we can have course 1, and course 2. But in order to take course 3, we have to pass both courses. Both course 1 and course 2. So it is something like this, right? So we have 2 answers, or 2 suitable orders to finish all of these courses. We can first take course 0, then 1, then 2, and then 3. Or we can take course 0, then course 2, then course 1, and then course 3. I told that because, based on these 2 arrays, right? Because the course 0 is a prerequisite for both course 2 and 1, and in order to take course 3, we have to pass 2 and 1. So we have two orders. And on the third example, the number of courses is 1 and the prereq array is null. So we do not have any prerequisites. So here the output would be 0 because we don't have any order. So it would be 0 or null. I hope you understood this problem better and in more details. If you still have problem understanding this problem, try to write several examples for yourself and write the suitable orders. This will help you to understand this problem better. Now that we understood this problem, I will talk about the suitable algorithm to solve this problem on the next section. The suitable solution of this problem is called topological sort, and it is based on graphs. So the first step to solve this problem is to model the prerequisites array into a graph. But the question is, how should we do that? So consider the number of courses is 7 and the prerequisites array is something like this. So we have 7 courses and here is the order of the courses. Based on the definition that the question gave us, now we can say that A is a prerequisite for F, E, and C, and also F is a prerequisite for E and G, D is for F, and B is for A and C. Now what do I want to do is to draw the suitable graph based on these dependencies. So we have this node and this is A. So this is the prerequisite for F and also E and C. Then F is for E, so there will be another H here, and F is also for G, so we have another node called G here, and F is a prerequisite for that, and D for F, so consider this is node D, and it is a prerequisite for F, and also B for A and C. So I put B here. It is prerequisite for C. And sorry, for C, so it is a prerequisite for C and also A. Okay, so this is kind of a graph that we have here. The next step is to figure out the in degrees of each node. You can say the in degrees is the independency degree or input degree, because let me write that and then explain it. So in degree, I just write in deg. Here the in degree is 1 because taking course A is just dependent on course B, so the in degree is 1 here. B, the in degree is 0 because in order to take course B, we do not have to take any other courses. For C, as we have 2 input edges, this is 2. And on the other nodes, I don't write in degrees. So here we have 2, again, A and D. And here we have 1, it is just F. Here we have 2, and here 0. Then we should use a queue. So consider this is the queue that we have. It is our queue, and we should first specify those nodes that have the in degree 0 and put them in the queue. Then we have to pop them from the queue and also remove them from the graph to specify the suitable order, which is our output. So let's go to solve it on this example. So the nodes that have in degree 0 right now are nodes B and D. So I should add them to the queue. I can write BD or DB, and you understand that the output would be different if I put D first or B first. So we understand that this problem does not have an unique answer based on the nodes that we choose to first iterate on. Okay, so for example, I first write B and then D. And at this level, I have to pop them from the queue and also remove them from the graph. So consider this is the output, which is the suitable order that we are searching for. So I pop B from the graph, from the queue, and also remove it from the graph. When I remove B from the graph, the degree of C would be 1, and the degree of A would be 0. So I pop it from the queue and write it on the output. Then I have to pop D from the queue. So I pop it and also remove it from the graph. So the degree of F will be 1 and D would be here. Now, which nodes have the degree of 0? Just A. So I put A here and then pops it from queue. But before I write here, I should remove it from the graph. So if I remove it here from the graph, F's degree would be 0, E would be 1, and C would be 0, 2. So I write it here. And now we have F and C, which have the 0 as their degree. So I just write them in the queue, F and C. And then I pop F from the queue and also remove it from the graph. So if I remove it, the degree of G would be 0, and also the degree of E. And yeah, then I have to pop C and remove it from the graph, as it is not connected to any other graph, so the degrees will be the same. I write C here. Now what do I have? I have E and G. These are the remained nodes, so I write them here, E and G. And then I pop E from the queue and also remove it from the graph and write it here as an output, and also pop G from the queue and remove it from the graph and write it here. So this would be a suitable output to take all of these courses. As I said before, this order could be different, so the problem does not have a unique answer. And also pay attention that if our graph has a cycle, we cannot reach to a suitable order to take all the courses. So if our graph is a directed cyclic graph, we do not have an answer. And to solve this problem and to this problem have a suitable answer, the graph should be DAG, or a directed acyclic graph. I hope you understood this algorithm, which is called topological sort. I mean, this is a way to solve topological sort. We also can solve it with DFS. On the next section, I will talk about the suitable code of this algorithm and also analyze the time and space complexity. Here we have a method called findOrder, and this method returns an array of integers, which is the output that we have here, the orders that we have to take the courses. This method takes two inputs. The first one is number of courses that we had here on the algorithm section, and also the prerequisites array. Then we build a map to model the graph in that, and also we have two arrays, two integer arrays, integrity, which shows the integrity of each node on the graph, and the topological order, which is the output that we have. And the size of both of these arrays equals to number of courses. In the first loop, we are modeling the graph using the map we just made, and by building adjacency lists. We also fill out the integrity array for each node, and then we make a queue to put the nodes with integrity 0 in them, just like the algorithm, as you remember. And we just add each node that the integrity of that node is 0 to the queue. Then we check the queue, we check each element of the queue until the queue goes empty, and remove those nodes from the queue, like here, and put them to the output, which is our topological order array here. So let me just review the whole scenario. We have to find those nodes that the integrity of those nodes are 0, and add them to the queue, and then pop them or remove them from the queue, and add them to the output. And by removing each node from the queue, we also remove that from the graph and update the integrity of its neighbors. So here's what we do in this loop. We just remove each node from the queue that we have, and we put it on the topological order, which is our answer. And then we check if our adjacency list, or the graph, contains that node, contains the queued node. So we update the integers of its neighbors here. So we just decrease the integrity of its neighbors, and if the integrity of those neighbors equal to 0, we add those neighbors to the queue. And at the end, we just check if we have covered all the courses that we had. So in this case, we return the topological order, which is the output that we had. And if we couldn't find any suitable order, we just return the null array. Now let's submit the code into LeetCode.com and see the results. So I just paste the code here, and here we go. So the code is accepted, and now I want to talk about the space and time complexity. As we pop each node with integrity 0 once from the queue, so the time complexity depends on V, which means vertices. And also, we iterate over all the neighbors of a node or a vertex. So that means we iterate over all the edges too. So the time complexity is an order of v plus e. The space complexity is also an order of v plus e, because in the worst case, we have to keep all the vertices with index 0 in the memory, and also as we model the graph with an adjacency list. So in other words, it means that we saved all the edges. So the space complexity is also an order of v plus e.
If you found this video helpful, consider subscribing and sharing it with your friends. And like always, stay tuned for more videos.